Okay, so today we're going to move on to section 4.3, and we're going to learn two more rules that are going to make taking derivatives so much easier, and they're also going to give us tools that will increase our repertoire of functions that we are able to take derivatives of. So the product rule and the quotient rule is what we're going to focus on today. Before we get to that, though, I want you to try and find, so if y equals x squared plus 6x times 3x minus 2, I want you to find dy dx. So pause the video, find dy dx, and unpause when you're ready to check your work. If you don't know what to do, then just wait a second and I'll go through the solution. Okay, so with what we know so far, in order to take the derivative of this, we have to multiply out these two binomials. So I end up with y is actually 3x cubed plus 16x squared minus 12x. Now I can take the derivative using my power rule, bring down the power, reduce the exponent, and I end up with dy dx equals 9x squared plus 32x minus 12. But there might be an easier way to do this. In this case, it's not much easier, but it's still an incredibly useful tool. So this is where we introduce what we call the product rule. So the product rule is if we have two functions, in this case I'm going to say u is f of x and v is g of x, then duv dx, uv is u times v, is u times dv dx plus v times du dx. Or I can rewrite it as duv dx is uv prime plus v u prime, or I could write this as u prime v plus u v prime. What it's saying is you're going to, well, let's just go through an example. It'll make a little more sense. So let's take the same example we have here. So instead of multiplying this out, what I'm going to do, let's follow this format right here. So I'm going to follow this format so you can follow along, but all of these, this, and this are essentially doing the same thing, or they are doing exactly the same thing. It's just writing it in a different order. So dy dx is going to be u, which is my first function. So I'm going to rewrite x squared plus 6x times the derivative of v. The derivative of v, so right now this is my v and this is my u, so the derivative of v is 3. And then plus, so I'll have plus v, so v is 3x minus 2, times the derivative of u. Well, what's the derivative of u? It's going to be 2x plus 6. So there is dy dx. Now in this case we would want to simplify this, and we'll end up with what we had on the previous slide. So this is going to be 3x squared plus 18x plus 6x squared plus 18x minus 4x is 14x minus 12. And when we combine like terms, we end up with 9x squared plus 32x minus 12. And notice again that is what we got on the previous slide. So two different methods to do the same thing. So now maybe you're saying, well, that wasn't really much easier. I still had to FOIL things out and combine like terms. How is this useful? Well, what if the like terms aren't as nice? So I want you to find f prime of f of x equals 2x plus 3 times 1 plus the square root of x. Pause the video, unpause when you're ready to check your work. Okay, so if I call this my u and this my v, I took u times the derivative of v plus the derivative of u times v. And now I can simplify, so 2x plus 3 times 1 half x to the negative 1 half is 2x plus 3 over 2 root x plus 2 root x. And we can leave our answer like that. So you can see maybe in this case it was a little nicer than multiplying this out because of that root x to use the product rule. Another example here where maybe we don't want to multiply this out because it's a trinomial and a binomial, so I want you to find y prime using any method you want. Pause the video, unpause when you're ready to check your work. Okay, so here I took the first times the derivative of the second plus the derivative of the first times the second. Now here I did have to multiply things out and combine like terms, so I end up with y prime is 5x to the fourth plus 36x squared plus 8x plus 27. You might notice that I might write or do the product rule in a different order sometimes. It really doesn't matter because it's multiplication and addition. So, you know, for instance, if I do v prime times u or u times v prime, it's the same thing. If I do the u prime and v first or the u and v prime first, it's the same thing because they're being added, so that doesn't matter. But you should fall into some consistent pattern for you, for you personally, so that you remember how to do the product rule. Okay, now we're going to move on to the quotient. The quotient rule. So the quotient rule is another rule that we can use if we're dividing two functions. So if I have du over v dx, it's v times the derivative of u with respect to x minus u times the derivative of v with respect to x over v squared. So now the quotient rule, it's very important the order in which you do things. It's important because subtraction is involved and the denominator stays in the denominator but it becomes squared. So now you need to remember the order in which you're going to do the division using the quotient rule. The quotient rule is very useful when we have something like this. So if we want to find the derivative of y equals 3x plus 1 over 2x minus 5, we want to use the quotient rule. So the way that I like to say it to myself, which I know you'll love to hear, because I'm going to say it to myself, but it's actually going to be out loud, so you're going to hear it. It's going to be bottom, so 2x minus 5, times the derivative of the top, which is 3, minus the top, 3x plus 1, times the derivative of the bottom, which is 2, over the bottom squared. So that's how I say it to myself, whether it's out loud or just in my head, with all of the other weird things that I say to myself in my head. Oh, wait, that was out loud, sorry. Now I'm going to simplify the numerator. So we get 6x minus 15 minus 6x minus 2 and then 6x minus 6x. So I get negative 17 over 2x minus 5 squared. I don't need to multiply out the 2x minus 5 squared because nothing's going to reduce with the negative 17 on top, so I can leave my answer like that. If you multiply it out, that's fine as well. So, I want you to practice. I want you to find the derivative of f of x equals x over x squared plus 1. Pause the video, unpause when you're ready to check your work. Okay, so again here I have the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Multiply out the numerator and combine like terms. So I end up with x squared plus 1 minus 2x squared over x squared plus 1 quantity squared. And so the numerator becomes 1 minus x squared and the denominator stays x squared plus 1 squared. Again, you want to see if something would reduce. I know 1 minus x squared would factor into 1 minus x times 1 plus x. but that's not going to reduce with x squared plus 1 quantity squared, so I can leave my answer like this. So now, sticking with that same function from the last problem, I want you to find the equations of the horizontal tangent lines for f of x equals x over x squared plus 1. Remember, you already found the derivative, so you don't need to do that again. So we know f prime of x is 1 minus x squared over x squared plus 1 squared. So again, I want you to find the equation of the horizontal tangent lines to the original function. You're going to need to use the derivative for that. Pause the video, unpause when you're ready to check your work. Alright, so you should end up with y equals 1/2 and y equals negative 1/2 as the equations of the horizontal tangent lines. So there are 2 horizontal tangent lines to this function. How do we come up with that? Well, we take the derivative and we set the derivative equal to 0. Why do we set the derivative equal to 0? Good question. We do that because the slope of a horizontal line is 0, and remember, derivative represents the slope of a tangent line. So if I want a horizontal tangent line, that means that the tangent line has a slope of 0. Now I solve this rational equation. Well, I can multiply both sides by the denominator and it goes away. So now I'm left with 0 equals 1 minus x squared, so x equals plus or minus 1. So what this tells me is these are the x values at which a horizontal tangent line occurs. So now I need to find the y value, because the y value is going to be the equation of the line, since a horizontal line is just written as y equals a number. So I take x equals 1 and x equals negative 1, and I plug it back into the original function, not into the derivative, but the original function. I know that plugging it into the derivative is going to just give me 0. So f of 1 equals 1/2, f of negative 1 equals negative 1/2, therefore y equals 1/2, and y equals negative 1/2 are the equations of my horizontal tangent line. Last example. Find the equation of the tangent line at x equals 1 for the function y equals x squared plus 4 times the quantity x cubed plus 4x over 2x plus 3. So here you can use a combination of the product and quotient rule when finding the derivative. Pause the video, unpause when you're ready to check your work. Alright, so you should end up with y minus 5 equals 7 times the quantity x minus 1. So that's the equation of the tangent line at x equals 1. Now, how do I come about that? Well, first I figured out what is y of 1. So I plug in 1 to the original function, and that's how I got 5. So that's how I know I was working with the point 1, 5. So that's where the 1 and the 5 came from in the equation of my tangent line. Okay, now I did the derivative. Now you had a choice here of multiplying out the numerator first, and then just using the quotient rule, or using the quotient rule and the product rule. I chose to do the latter, so I used the quotient rule and the product rule. It did not necessarily make this easier. In fact, it might have made it more difficult if I was actually trying to simplify the derivative. But since all I needed to do was find the equation of the tangent line, I did not have to worry about simplifying. I can just plug in 1. So here it goes. This is the bottom times the derivative of the top. So for the top, I did the product rule. So I did the first times the derivative of the second plus the derivative of the first times the second. Now I have minus the top, so now I'm back to the quotient rule, times the derivative of the bottom over the bottom squared. So now I can substitute in the 1 for x to find, so I'm finding y prime of 1 to find the slope. These are all fairly simple calculations, and I end up with y prime of 1 equals 7. So that's how I got y minus 5 equals 7 times the quantity x minus 1. So this is actually a really good example of, was it easier to use the product rule or not the product rule? Well, in this case, it might have actually been easier to not use the product rule, to multiply this out first, because if I actually had to simplify this derivative, I would have needed to multiply that part out anyway. But because I was just trying to evaluate it at a value, or at 1 in this case, it didn't really matter. So I just wanted to show you that you can use multiple techniques at once by, in this case, using the quotient rule with the product rule. And in fact, there will be situations where you have to do that. So you want to understand how to do that. Alright, so we want to make sure we understand the product rule and the quotient rule. Great lesson.